Core 3 Review Sheet I Trigonometry 1. Generally, the questions on this video are different from those on the review sheet, but if you work your way through the video, it will help you to answer the review sheet. We're starting by sketching a graph of y equals sine to minus 1 of x. Start by looking at the sketch of y equals sine x. Notice it is a many-to-one function, and we want to do an inverse, and you can't do the inverse of a many-to-one function. So what we have to do is restrict the domain of y equals sine x so as to make it a one-to-one function. So to do that, we're going to stop at minus pi over 2 here and pi over 2 here. Now it's worthwhile actually looking at this and saying, well, what are the end points going to be? So this is going to be minus pi over 2 minus 1, and this is going to be the point pi over 2, 1. If we now look at the actual inverse function, you're going to be swapping the coordinates round. So it's going to be 1 pi over 2 at this end, minus 1 minus pi over 2 at this end. Where it's horizontal here, it's got to become vertical. Where it's going through the origin, it's got to stay going through the origin. So what you're going to get is a graph still going through the origin, whereas the x-axis had gone minus pi over 2 to pi over 2, notice it's now the y-axis going from minus pi over 2 to pi over 2. Where the y-axis had gone minus 1 to 1, the x-axis goes minus 1 to 1. Notice in particular that the coordinates are going to swap around the x and the y coordinates at those end points. So here, where it was pi over 2, 1, it becomes 1 pi over 2. And where it was minus pi over 2 minus 1, it becomes minus 1 minus pi over 2. Horizontal at these points, vertical at these points. Okay, let's have a look at the next question. You're finding in radians the exact values of. Now, you might be able to do this just straight from your calculator. But if not, it's worthwhile actually looking at where these come from. And they come from two special triangles. The first is a triangle which is an isosceles right-angled triangle. If we've got lengths 1 and 1, by Pythagoras, 1 squared plus 1 squared, 2, square root it, that length's root 2. So you'll see that sine of 45 degrees is 1 over root 2. Indeed, cos of 45 degrees is also 1 over root 2. So if we're doing sine to the minus 1 of 1 over root 2, you're going to get 45 degrees. If we wanted in radians, 180 degrees is pi radians. This is a quarter of 180, so it's going to be a quarter of pi, pi over 4 radians. Cos to minus 1 root 3 over 2. This comes from an equilateral triangle which has been cut in half. So it's going to be a right-angled triangle now, but the length of the sides where they were 2 on each side is 2 here, but only 1 here. By Pythagoras again, 2 squared minus 1, 3, so this is root 3. Now we want the cos to be root 3 over 2, so you need to be looking at the 30 degrees, so adjacent over the hypotenuse is equal to root 3 over 2. So cos to minus 1 of root 3 over 2 is going to be 30 degrees. And that is 1/6 of pi. 6 thirties making 180, so it's going to be pi over 6. Next one, cos to minus 1 of minus root 3 over 2. Well, now we need to move into the second quadrant. If you think of your cos graph, then you need to be moving past the 90 degrees, and it's going to be 180 degrees minus your 30 degrees, and that gives you 150 degrees. Cos of 150 is minus root 3 over 2. That is 5 lots of your 30, so it's going to be 5 times your pi over 6. Give the exact value of cosec 240 degrees. Well, cosec is 1 over sine. So you're going to be using cosec 1 over sine. So let's look at sine 240. Well, sine 240 is minus sine of 60 degrees. It's going to be, sine is negative in that position. So it's sine of 60. If we go back over here, you'll see sine of 60 is opposite of hypotenuse root 3 over 2. So minus sine of 60 minus root 3 over 2. And cosec of it is going to be 1 over that, the reciprocal of it. So it's going to be 1 divided by root 3 over 2. That's going to be, 1 divided by minus root 3 over 2, so it's going to be minus 2 over root 3. If you want to rationalize it, multiply top and bottom by root 3, and you get minus 2 root 3 over 3. Question 4, the proofs. So let's look at these. These are ones that most people have difficulty with. You need to be quite careful with how you do them. So we're going to start by trying to prove that sine theta tan theta plus cos theta comes to the same as sec theta. Now don't be in too much of a hurry to turn the sec here into 1 over cos. Let's start with the left-hand side and try and get everything in terms of sines and coses. Okay, now you should know that tan theta is equal to sine theta over cos theta. So where we have a tan theta here, let's put it as sine theta over cos theta. So your left-hand side now becomes sine theta, stays the same. Instead of tan, sine over cos, cos theta staying the same. Okay, now if we actually now multiply, you're multiplying sine over 1 times sine over cos. So you're going to get that this side here is sine squared theta over cos theta. Sine times sine, sine squared over cos. That stays as plus cos. This is a fraction. So in order to add this part on, we need a common denominator. And the denominator is going to be the cos theta. So you're saying, well, right, I want a cos theta below here. So this is cos theta over 1. If I multiply the denominator by cos theta to get cos theta, I multiply the numerator by cos theta, I get cos squared theta. So you're saying this cos theta is the same as cos squared theta over cos theta. Denominator is the same. We can add the numerators. It's using the same rules as you'd use just with ordinary fractions. So you get sine squared theta plus cos squared theta over cos theta, and then you should instantly spot sine squared plus cos squared is 1. So we can replace it, the sine squared plus cos squared by 1 over cos theta, and that is what is equal to sec theta. So our way through, turn the tan theta into sine over cos, then simplify this, sine squared over cos, get a common denominator, so this stayed the same, multiplying here by cos over cos gives you cos squared over cos, and then combine the numerators and use the rule that you know for sine squared plus cos squared, and then it all comes out. Let's look at another example. This time you've got a multiplication of a part in brackets and another part of brackets equaling tan squared plus sine squared. So let's just look at this left-hand side, and if you've got two brackets being multiplied together, then let's actually multiply them out. But to do this, remember, a plus b times a minus b is a squared minus b squared, difference of two squares. Here you've got an a plus a b, and there an a minus a b. So you're going to end up with sec squared minus cos squared, sec squared minus cos squared, because the other bits will cancel out. The other bits come to minus sec cos plus cos sec, same thing. Okay, so they'll cancel out. So this multiplies to sec squared minus cos squared. Then we don't want any sec squareds over here. We, for that matter, don't want the cos squared. But let's get rid of the harder part of the sec squared first. You should know the identity that sec squared is 1 plus tan squared. That's good because tan squared is one of the things we need. So we replace the sec squared by 1 plus tan squared. So you get now 1 plus tan squared minus cos squared. The sec squared is turned into 1 plus tan squared. Now we need to say we've got tan squared, we don't want 1 minus cos squared, we want sine squared. So think of a connection between sine squared and cos squared. Again, use sine squared plus cos squared is 1. You've got 1 minus cos squared. Well, if we do 1 and we minus the cos squared, that is equal to the sine squared. It's just rearranging this equation. So you get that 1 minus cos squared, that part, can be replaced by the sine squared, and then you've got there that this is equal to your tan squared plus your sine squared. Okay, so some proofs quite quick, others can be a little bit hard, but all the way through you need to be looking and thinking, what identity can I actually use, and also actually have an eye on what your answer is so that you know what you're working towards. Okay, good luck.